Good afternoon, ladies and gentlemen. I'm Peter Goddard, Director of the Institute for Advanced Study, and it's my pleasure to welcome you here this afternoon to this Institute lecture. After the lecture, there'll be a reception to which you're all invited in Ford Hall. Today, our speaker is Scott Tremaine, who joined the Institute as Richard Black Professor in the School of Natural Sciences in January 2007. Scott obtained his bachelor's degree from McMaster University in Ontario in 1971 and his PhD from Princeton University in 1975. He held postdoctoral positions at Caltech, at Cambridge University, and for 3 years here at the Institute, before becoming an associate professor at MIT in 1981. In 1985, he moved to become the founding director of the Canadian Institute for Theoretical Astrophysics and a professor in the University of Toronto. In 1997, he came to Princeton as a professor in the university's Department of Astrophysics, serving as its chair from 1998 to 2006, and becoming Charles A. Young Professor in 2002. Scott has very many distinctions and awards to his name, including honorary foreign membership of the American Academy of Arts and Sciences, fellowship of the Royal Society of Canada and the Royal Society of London, and membership of the National Academy of Sciences. He is one of the world's leading experts on astrophysical dynamics, including the formation and evolution of planetary systems, comets, black holes, star clusters, galaxies, and galaxy systems. Today's title is The Fifth Element, Astrophysical Evidence for Black Holes, Dark Matter, and Dark Energy. Scott.
Thank you. In order to start, I'd like to give a very quick 10-minute run through the entire history of astronomy and astrophysics, starting with the Greeks. As everyone knows, in Greek philosophy, the material on the Earth was divided into 4 elements: earth, air, fire, and water, which were subject to change because of the complex phenomena on the Earth. But in addition, at least according to Plato and Aristotle, there was a 5th element, the ether, which was found only in the heavens and which was immutable and unchangeable. This was reflected, at least to some extent, in Greek astronomy, which of course was geocentric. The Earth was at the center of the universe. It contained 8 spheres, 7 holding the known planets, and the last holding the stars, which were surrounded by this immutable ether. The next major change in our outlook on the universe came in the Middle Ages with Copernicus, a Polish astronomer who argued that the sun, rather than the Earth, was the center of the solar system. In these little cartoons, Plato's view with the Earth at the center and the sun orbiting around it is replaced by one with the sun at the center and the Earth orbiting around it. The importance of Copernicus's insight was not just the fact that he completely revised the geometry of the solar system, but also that he demoted the Earth from being the center of the universe. It was now, instead of being the center, just one of many planets orbiting the sun. And this was such a major change in our view of the universe that it's come to be encapsulated by astronomers in what's called the Copernican principle, which says we're not located at a special place or a special time in the universe, and any time you have a model of what's going on in the universe that makes our current location special or the current time special, then it's probably wrong. The next step after Copernicus was Newton, who famously deduced the law of universal gravitation while sitting outside this house under this apple tree, and he was inspired when he saw an apple fall to Earth, although not this apple. Newton's insight was that the law of gravity that caused the apple to fall to Earth was the same law that governed the motion of the moon and planets, that they were falling in precisely the same way. One of the consequences of this was that the speed of a planet declines with its distance away from the sun, a prediction which was known to be true as an empirical fact. And again, the importance of Newton's insight was not just the fact that he understood the dynamics of the solar system, but also that he recognized that the laws of physics that can be investigated in the laboratory should also apply and can be used to describe the behavior of the stars and planets. That is, that what we learn by experiments on Earth can be applied to the heavens. The next step in in understanding the nature of the heavens came from looking at spectra of the sun. As you're familiar with, in the case of a rainbow, either a glass prism or droplets of water can disperse the light from the sun into its constituent colors. And the person who looked at this most carefully was Joseph Fraunhofer. Using a prism in his laboratory in sunlight, he discovered that the light from the sun was interspersed with very fine, dark, narrow lines. Not only did he find these lines, now called Fraunhofer lines, he recognized that they were a property of the sun rather than the Earth's atmosphere. And he also noticed that if he looked at the spectrum of a flame from a burning substance in his laboratory, he could see some of the same spectral lines. And he concluded that each chemical element is associated with a set of spectral lines, and the fact that the dark lines in the solar spectrum are the same as the dark lines that you see in flames in the laboratory means that the sun is composed of the same elements as the Earth. And this insight has been extended. This is a modern solar spectrum, which should be read like a book. That is, it's been split up so that you read across the lines in the same way you would read a book. Not only did did the solar spectra show that the sun was composed of the same elements as the Earth, but it also led to new discoveries. In particular, later in the century, some Fraunhofer lines were discovered that weren't associated with any known element. And the spectroscopists who discovered these lines said that they must be associated with some new element that had not yet been discovered on Earth, and they proposed to call it helium. This was actually how the element helium was discovered. It was only isolated on the Earth some 30 years later. And the lesson of this, for the first time, was not just that physics can tell you how the heavenly bodies behave, but that studying astronomical objects can teach you about new physics. Although the sun is made of the same elements as the Earth, it's not made in the same mix. It's now realized that the mix of elements in the sun is very different from the Earth, presumably because of loss of elements during the formation of the Earth. The sun's 75% hydrogen, 23% helium, and all the other elements in the sun only comprise about 2% of its total mass. This is true for other stars as well. And it leads to the conclusion that hydrogen and helium are by far the main constituents of the universe in roughly a 3-to-1 ratio, with all the other elements heavier than hydrogen and helium being only a minor pollutant on these two elements. This discovery was actually made in a wonderful PhD thesis at Harvard by Cecilia Payne. Not only is she famous for this insight, but she also played an important role in the gradual acceptance of women as academic researchers in the United States in the 20th century. She got the first PhD in astronomy from Harvard. She was the first woman promoted to the tenured faculty at Harvard and the first one to head a department at Harvard. Once astronomers understood that what the constituents of the stars were, they began to think even more ambitious thoughts and began to wonder about the formation of the elements themselves. This is a remarkable act of hubris or chutzpah, to think not only that you can understand the nature of the elements in the universe, but where they came from. It almost treads on theology. And an example of how revolutionary it was is a nice quote from Charles Darwin, who of course was thinking about speciation and the theory of evolution. Somebody asked him if he had thought about the origin of life itself, and he said, "It's rubbish thinking at present of the origin of life. One might as well think about the origin of matter." But in fact, in the intervening century and a half, astronomers have thought about the origin of matter, and we now know much more about it than we do about the origin of life. So the way to think about the origin of matter is to go back to the periodic table that you saw in chemistry classes in high school. It organizes all of the elements in terms of their atomic number, starting with the lightest element, hydrogen, then helium, and working their way up to elements with atomic number of about 100. And you can use spectroscopy to determine the relative abundance of each of these elements in the stars. And what you find is that the abundance as a function of the atomic number exhibits this remarkably rich and detailed structure. The abundances of the elements vary over factors of 1,000 million, about a billion. And there's this remarkably detailed sawtooth structure with some elements relatively common, some extremely rare. And it's a tremendous challenge to try to understand why this peculiar and rich behavior should have developed in the formation of the elements. In order to talk about this, I want to just remind you of the neighborhood that the sun resides in. When you look at the sky on a dark night, not so easy in New Jersey, you see a band of light crossing the sky, which is the Milky Way. The Milky Way is visible both from the northern hemisphere and from the southern hemisphere. If you look at the Milky Way with a telescope, it resolves itself into a vast number of stars. And in fact, the Milky Way consists of the stars in our own galaxy. The reason it has this curious sort of mottled appearance is because the stars are accompanied by small particles of what you might think of as smoke or dust, just small solid particles. That means that in effect we're looking at these stars through a swirling kind of fog. And sometimes you look at an area like this one through a fairly dense part of the fog, or even denser parts here, and other times you can see much further away, and that gives it this irregular appearance. I've just pointed out here two other smaller galaxies that are satellites of our own galaxy, the Large and Small Magellanic Clouds visible in the southern hemisphere. They'll reappear in the story a little later on. Because of this fog and smoke, we can't see all the way to the center of the galaxy, but we can do better if we use, rather than visible light, infrared light, for the same reason, really, that the Army uses infrared detectors for looking through fog and smoke on the battlefield. When you do that, you can get images like this. This is a picture of the whole sky flattened down onto the plane of the screen, showing the center of the galaxy here, still some dust, but a much clearer view than we get in visible light. The disk of the galaxy here, if we were looking at the galaxy from outside, the sun would be about here, and there's one of the Magellanic Clouds. The total number of stars in the galaxy is about 100,000 million stars, and the Milky Way is just a typical, ordinary, middle-class galaxy. We see many other galaxies similar to that at much larger distances from us. In addition to these small solid particles in the stars, galaxies like the Milky Way contain gas as well. Mixed in between the stars and these dust particles that give these dark lanes is about 10% of the same amount of mass in just gas between the stars. That gas slowly cools off, gravitationally clumps, and forms new stars. So the reason that we see relatively young stars in here is because stars are constantly being formed in the galaxy. Not only are they being formed, but old stars die, and occasionally the most massive stars die in a very violent way through an enormous explosion called a supernova. This is an example of a supernova in a distant galaxy. You can see the image of the galaxy before the supernova, and then the light from the supernova, which temporarily, at least for a period of a few weeks or months, outshines the combined light of all the other stars in the galaxy. This supernova was a very long way away. You have to look a long way away because they're very rare, but you do occasionally have supernova in our own galaxy. The most recent one nearby was in the Large Magellanic Cloud. It went off in 1987. This is what the star looked like before it went supernova. There was no obvious sign that something dramatic was going to happen, but all of a sudden it blew up. Became so bright that it was discovered because a graduate student working at night at an observatory walked outside, looked up at the sky and said, "Oh my gosh, there's a bright star there that I've never seen before." Supernovae have also been seen in our own galaxy, but only in historical times. This is the glowing gas cloud left over from a supernova that went off in 1054 that was recorded by Chinese and Arab astronomers and also probably by Native Americans. The reason that supernovae are important for the origin of the elements is that all stars, including the sun, make their energy by nuclear reactions. Nuclear fusion is the source of the energy that powers the sun. This has been known on a theoretical basis for many decades, but there's actually remarkably direct evidence that nuclear reactions are going on. One piece of evidence is that the nuclear reactions in the core of the sun produce small particles called neutrinos that interact very weakly with matter and therefore can travel right out of the core of the sun through interplanetary space and through the Earth as well. They're occasionally detected by large experimental detectors in underground laboratories, such as this one. It's basically just a huge globe filled with very pure water. Occasionally, when a neutrino goes through it, it emits a flash of light when it interacts with the water, and those flashes are detected by an array of photocells surrounding the water. We know that the rate at which neutrinos are coming through the Earth is exactly the rate that's required in order for the sun to burn with the brightness that it has. If the sun, for some unknown reason, turned off its nuclear reactions tomorrow, it would take 1 million years for it to cool off enough to make a difference to us on Earth, but these experiments would know within a matter of minutes. So they have direct evidence that the nuclear reactions are occurring right now. Moreover, if you look at supernovae, the light that comes out of one of these brilliant explosions declines exponentially with time, here over a period of 2 years. And the rate of decay is exactly the rate of decay that you would expect for radioactive cobalt. We know that radioactive cobalt is produced in vast quantities in a supernova explosion, and the radioactive decay of this newly minted cobalt is precisely what's producing the long tail to the light curve of the supernovae. And finally, some stars show Fraunhofer lines of a particular element, technetium, number 43. Technetium, it happens, has no stable form. The longest lived isotopes of technetium only last about 1 million years. That says somehow they must have been formed in the star within the last 1 million years, and they must have been formed through ongoing nuclear reactions in the stars. These nuclear reactions, like any burning process, produces ash. As the nuclear reactions go on, the hydrogen and helium in the star is gradually converted into heavier elements. And the great insight that astrophysicists had in the 20th century was that it may be that all of the elements that we know of beyond hydrogen and helium were produced in the centers of stars. They were produced in the process of stellar burning, then these stars went supernova, expelled the material into the interstellar gas where it was mixed with the primordial gas, reincorporated into stars, and then the process continued through a second and third generation. This makes quantitative predictions. It says that initially the star was composed only of hydrogen and helium, which is why they're so abundant. The dip in abundances for these elements is because they're known to be destroyed in nuclear reactions in stars. The gradual decline with increasing atomic number is simply because you have to build these elements up gradually through more and more nuclear reactions in the interiors of the stars. The peak at iron is because iron's an exceptionally stable iron element, and it's the natural ash that's produced by nuclear reactions in very hot environments. And finally, this kind of sawtooth pattern arises because it turns out the nuclei with odd atomic numbers are less stable than those with even atomic numbers, and the more stable ones turn out to be more abundant. So burning nuclear reactions in stars explains all of the origin of all of the elements except for hydrogen and helium. For those, we have to seek a different explanation. But everything other than hydrogen and helium was made deep inside stars. All of the material in this room, the atoms that you're made of, except for the hydrogen, all came from the deep interior of some past generation of some past star which exploded. A more poetic way of saying this is that we really are stardust. In order to talk about the origin of hydrogen and helium, we have to talk a little bit about cosmology. The most basic fact in cosmology is that the universe is expanding. Galaxies that are about 10 million light years away from us are receding from us at about 2,000 kilometers a second. At 100 million light years, they're receding 10 times as fast. If you extrapolate that expansion backwards, it says that the universe must have emerged from a singularity, the Big Bang, which occurred about 14 billion years ago. The dynamics of the universe is determined by Einstein's theory of general relativity, and Einstein's theory tells us that the geometry of the universe is related to the overall density of matter and matter content in the universe. Einstein tells us that there's a critical density. If the average density is now less than the critical density, the universe is infinite and will go on expanding forever. If it exceeds the critical density, the universe is finite. And the critical density is actually quite low. It's about 1 atom per cubic meter, but nevertheless, there's a lot of cubic meters in the universe, and even that very low density is sufficient to eventually make the universe close over on itself and remain finite. When you follow the evolution of matter back towards the Big Bang, at earlier times the universe was smaller, and so it was denser and hotter. And if you follow the physics back right to the Big Bang, what you discover is that in the first 3 minutes of the universe, copious amounts of hydrogen and helium and almost no heavier elements would be produced from the kind of primordial soup that existed right after the Big Bang. So it seems almost certain that all of the hydrogen and helium that we see in the stars and in the universe was created as part of the Big Bang. Moreover, the Big Bang produces trace amounts of other elements, and you can compare the relative abundances of hydrogen and helium in the trace elements for different models of what happened after the Big Bang. You find that the relative abundances are strongly dependent on the density of matter now or after the Big Bang. And what you find is that the correct relative amounts, for example, 23% helium as you see in the sun, are all obtained for all these different elements if and only if the density of matter in the universe at present is exactly 4% of the critical density. So we don't know why that 4% is correct, but we're very confident that getting the relative abundances of the elements in the universe correct requires that the density of matter has this precise ratio to the critical density. I put up this book cover simply because this was really nicely described in a book written by Steven Weinberg with the famous title, The First 3 Minutes, because in his view that was when almost all of the properties of the universe were determined. So that kind of ends the very quick summary of of the history of astrophysics, and to summarize it, the Copernican principle says that we're not located at a special place in the universe or a special time in its history. The laws of physics we investigate in the lab also govern the behavior of astronomical objects, and that in reciprocity, the study of these objects can reveal new laws of physics. The sun and the stars are made of the same elements as the Earth, and these elements were some made in the Big Bang and some in nuclear reactions in the centers of stars. And this synergy between physics and astronomy, of course, is the reason why the discipline of astrophysics emerged as one of the most interesting subjects in science through this merger of astronomy and physics. So this is a wonderful success story. However, around the middle of the 20th century, some of its successes began to unravel. Some of the first clues came from looking at the rotation speed of stars in galaxies. You can measure the rotation of a star like the sun around the center of a galaxy. And just as Newton predicted from universal gravitation for the speeds of the planets as you went out from the sun, once you get out to the outer parts of a galaxy, the speeds of the stars in the outer parts of the galaxy should fall off in precisely the same way that the speeds of the planets fall off from the sun. The answer is that they don't. Instead of falling off like this, the speeds at which stars go around, typically maybe 100 or 200 kilometers per second, remain flat and independent of radius and don't fall off. This is a schematic view. This is actual data, which shows the discrepancy between what you'd expect and what you actually see. It emerged that there are only two possible explanations for this that are consistent with all the data. Either Newton was wrong. For some reasons, his law of gravity doesn't work on the scale of galaxies, even though it seems to work extremely well in every context we've been able to test it. Or the galaxies must have some vast amounts of matter, at least 2 or 3 times as much as they have in stars and gas, sitting in their outer parts, which are putting an additional gravitational force that's keeping the rotation speeds high. Well, this is such a remarkable and surprising conclusion that you go looking for more evidence. Other evidence comes from satellite galaxies of our own. In addition to the Magellanic Clouds, our galaxy is surrounded by several dozen small satellite galaxies before you get out to the next big galaxy, the Andromeda Galaxy. These galaxies are very small. They have typically only somewhere between 1,000 and a few 100,000 stars, many orders of magnitude less than the Milky Way. In some cases, like this one and this one, their star density is so low that you can hardly convince yourself that you're seeing something there. Nevertheless, you can measure the velocities of these stars in the same way that you measure velocities of stars in much larger galaxies. You can use Newton's laws to calculate the amount of mass that's in the galaxies to give the stars their motions if they're in equilibrium. And what you find is even more remarkable, that these galaxies have up to 100 times more dark matter than they do in stars. Not just 2 or 3 times, but 1 or 2 orders of magnitude more than you'd expect just from the things that you can see. So there's dark matter in very small galaxies. There also turns out to be dark matter in very large systems. This is a cluster of galaxies. What you're seeing is a whole set of point-like sources that are foreground stars in our own galaxy. If you look past the intervening stars in our own galaxy, you see these large, fuzzy, sort of yellowish and bluish galaxies. These are all at roughly the same distance. They're part of a cluster of galaxies. They're orbiting around one another as a result of their mutual self-gravity. Clusters are some of the largest equilibrium structures in the universe. And once again, if you believe Newton's laws, you can apply these laws to calculate the mass that must be there to hold the cluster of galaxies together and compare it to the mass that you know is in the stars in these objects. And when you do that, you find that the masses of every cluster that you look at is about 5 times as large as the total mass you can ascribe to the stars and gas in the cluster. Again, a remarkable conclusion. You'd like to have some independent evidence that it's correct, and fortunately, there is such evidence. This is an example of a rather distant cluster of galaxies. All of the kind of yellowish objects are galaxies in the cluster. A few bright objects with the spikes rising from the optics of the telescope are foreground stars. But you also notice these curious blue objects sprinkled around the cluster. And somehow they all look kind of strange. If you expand the images and sort of squash them in the right way, you get images that look like this. And not only do these look a little strange, but they all look the same. That is, each one of the images has a big blob here. It's sort of ring-like, and it has a little extra structure here. The reason these images all look the same is that they're all the same object. What's happened is that according to Einstein's theory, mass can bend light. And this cluster has enough mass that it's acting like a giant lens and imaging a galaxy that happens to lie at a much larger distance far behind it and creating several separate images of the galaxy. Now, this is not a lens that you'd like to have in your glasses. You don't want 5 images of everything, but gravity, isn't designed to make good images, and so you often get multiple features like this. You can understand this in a little more detail by imagining a thought experiment in which there's mass here, and this source in green goes past it. The blue marks the images that you'd get of this source that coincide with the source at large distances, but the images split and move away as it crosses close to the lensing mass. So this extra mass has 2 effects. It distorts the image and splits it into two, and it can also magnify the image so that the brightness of the combined images goes through a characteristic curve like this. If the source was exactly behind the lensing mass, so the U and the lensing mass and the source were along the same line, then the source wouldn't provide two images, it would be split into a perfectly symmetrical ring, which is called the Einstein ring. In the case of the cluster that we looked at, the motion of the foreground and background galaxies, of course, only occurs over cosmic times. It's much too slow to see any motion. But to get some idea of how it actually behaves, you can make a movie in which you take a whole set of background galaxies, which you can think of as wallpaper, and slide them past the intervening cluster. You can see this. You can sort of see hints of the Einstein ring here. It's not perfect because they're never precisely in line. You can see some distortions as the galaxies go past individual foreground galaxies, but most of the distortion is from the cluster itself. And because we understand how much mass bends the light, we can use this to determine the mass of the cluster. Could you go to the next slide, please? Okay, so you can use that to get an independent measurement of the mass of the cluster. The mass agrees with the mass that you determine from the motion of the galaxies in Newton's law of gravity. So we have very firm evidence that in these extremely large systems, the total mass is about 5 times the mass that you can ascribe to the stars and the gas. So the conclusion from all of these results is that every measurement we make of galaxies and galaxy clusters on large scales shows that the mass in stars and gas is only a fraction of the total mass. The conclusion must be that the vast majority of the matter in the universe is in some unknown and invisible form, and the next natural question is, what is it? Well, in principle, it could be rocks. That's not very likely because we know most of the mass is probably hydrogen and helium, and it's hard to make rocks out of hydrogen and helium. Could be very faint stars, so faint that we can't detect them, although many people have looked and not discovered them. It could be planets, although those are usually found around stars. And of course, they could be black holes, which are, of course, very good at hiding themselves. The best way it turns out that the key for figuring out which, if any, of these possibilities is correct is once again gravitational lensing, but this time not of galaxies by clusters of galaxies, but of stars or other objects by other stars. Now, because the mass of a star is so small compared to the mass of a galaxy, the image splitting that you get is much too small to detect. But the magnification that you expect from the lensing is still present. Moreover, the size of the Einstein ring is so small that you can expect to see that traversal of the Einstein ring if you monitor a star for a few weeks or months. Whoops. The way this works, again, is that you're watching the change in the brightness of a star as it is lensed by an intervening object. You can detect these events. This is an example of real data showing a curve that looks exactly like this. Now, if you're going to try to find these, because these are such rare events, you want to look somewhere where there's a lot of background stars. The two best places to look are either the center of the galaxy, where there's a vast number of stars, or the Magellanic Clouds. And astronomers have looked at both places. Basically, what they do is they pick a field of view and they simply stare at it every clear night for month after month, looking for events like this that take place over a few months. If you look at the geometry, if you look at the center of the galaxy, you're looking through an intervening set of stars here, and so you should see gravitational lensing by the intervening stars, and that provides a check on whether your method is working because you know the stars are there. If you look at the Magellanic Cloud, because it's a long way from the disk of the galaxy and there's not very many stars here, but there's a lot of dark matter, then if the dark matter is black holes or planets or very faint stars, you should see gravitational lensing by the dark matter. The conclusion is that you do see stars lensed by intervening stars if you look in this direction. You don't see stars lensed in this direction, and the conclusion is simply that the dark matter between us and the Magellanic Cloud can't be any of these can't be any of these. So conclusion number one is that since we don't see any gravitational lensing from the dark matter in the Milky Way, it can't be any compact object like this. But there's a second, even more powerful argument. We know that you only create the right amount of helium in the Big Bang if the density of ordinary matter is 4% of the critical density. But when you go out and look at all these clusters of galaxies, the average density of the dark matter is 5 times larger, or about 20% of the critical density. That means that the dark matter can't be any of these, or in fact can't be any object, no matter how strange, that's made out of ordinary matter, because then you'd get the wrong amount of helium in the sun. The conclusion is that the dark matter has to be some sort of exotic form of matter that's never found on Earth, never seen in the stars, has never been created in any laboratory or experiment or accelerator. It must be some exotic and completely unknown form of matter, probably some as yet undiscovered elementary particle that was produced in huge amounts in the Big Bang. Trying to find this particle is one of the major themes of experimental physics and astrophysics in the next decade. There's an armada of different experiments that are trying to find it. The Fermi Gamma Ray Space Telescope is looking for gamma ray signals from dark matter in the halo of the galaxy. It was launched last spring. There are dark matter searches where you bury an extremely sensitive detector in an underground mine and look for occasional interactions with dark matter particles from the galactic halo. It's possible that the Large Hadron Collider, which is being turned on this fall and winter in Geneva, will produce some of the dark matter particles. The most exotic experiment is called IceCube. It's an experiment that's being set up at the South Pole, in which they use the Antarctic ice cap as a giant detector. They basically pump hot water down holes, melt the ice, drop a string of detectors down the hole, let it refreeze, and then monitor throughout the year the Antarctic ice, looking for flashes of light from dark matter particles that are interacting with the ice. Okay, well, we don't know what the nature of this exotic dark matter is, but we can still work with it. We know that the total density of matter is 25% of the critical density, and as I said before, Einstein's theory tells us that the geometry of the universe is determined by its dark matter content relative to the critical density. If the density is above the critical density, the universe is finite. A two-dimensional analog of the curvature of space looks like this. A more proper statement is that if you send two people off in opposite directions, eventually the distance between them will be less than you would expect if space were flat. If the average density is less than the critical density, this is a more appropriate representation. If it equals the critical density, then space is flat, just the kind of flat space that we're familiar with. Moreover, since it's ordinary matter and mass is conserved, we can calculate how that density varies relative to the critical density earlier in the universe, and so we can deduce the expansion history of the universe. So we can, if we assume that this is the correct inventory of the constituents of the universe, we can calculate what the geometry of the universe should be and compare it with observations. One way to do this is to look at the relation between distance and brightness for supernovae, because these supernovae seem to all have the same peak brightness. And we know that in a flat universe, the brightness of a standard source of light falls off like 1 over the square of the distance. So this plots, for example, the distance to these supernovae against their brightness. This is a somewhat expanded plot which shows the prediction that you would make in the model I've described, where the total matter density is 25% of critical. You can see that it works pretty well, although I have to say, it kind of looks like it's a little high here. You can also look at the large-scale distribution of galaxies. We now have surveys of the distribution of galaxies that have millions of galaxies in them, tens of millions of galaxies in them. The galaxies are not distributed completely at random, but rather they show correlations that can be analyzed statistically and that depend on the history of the universe. Could you run the video, please? So this is, whoops, let's go back. Let's try that again. Just click on it. So this is a imitation voyage in which we start at the sun and move outwards from the sun at an ever-accelerating speed. And all of the galaxies, I mean, each of these represents a real galaxy. These are all galaxies that have been measured in this particular survey, the Sloan Sky Survey. And what you should look for is patterns in the distribution of galaxies. You shouldn't be distracted by the fact that you see some streaks here. That's because the survey doesn't cover the whole volume of the sky, simply because it was taken from New Mexico and some parts of the sky aren't accessible from New Mexico. So as you look at this, you can start to see what look like filaments here and here in the distribution of galaxies. This is just rotating the distribution. The filament here, voids where there are relatively few galaxies, and a curious sort of web-like or bubble-like structure in which there are areas of high density of galaxies surrounding low densities and areas that almost look like filaments. All of these properties are determined by how galaxies cluster and form in the expanding universe, and if they're analyzed correctly, they tell you what the geometry and the history of the universe has been. You can also look at the age of the universe as measured from the oldest stars and compare that to what you would expect from your model of the history of the universe. You can also look at small irregularities in the background radiation left over from the Big Bang. The answer is that all of these independent estimates all agree that the correct model is that the universe is flat. That's good because it means you don't have to pay a lot of attention to trying to understand geometry in curved space, which I always find difficult. What's maybe not so good is that since the universe is flat, Einstein's theory then says that what we've identified, the ordinary matter and the exotic matter, is not sufficient. There must be something extra containing almost 3 times as much matter as we've identified in order that you add up to 100% of the critical density. That remaining 76% is variously known as dark energy or cosmological constant or vacuum energy. Most likely it's simply the quantum energy associated with empty space. The idea of a cosmological constant was first introduced by Einstein as a kind of ad hoc modification to general relativity in which he just took his standard general relativity equations and added this extra term. He famously called it his biggest blunder, although I think that wasn't because he didn't believe it could be correct, but because he introduced it as a repulsive term to balance the attraction of gravity so that you could have a static universe. And shortly after he'd done it, Hubble discovered that the universe was expanding, and what Einstein was kicking himself for was the fact that if he'd had the courage to stick with his original equations, he could have predicted that the universe had to be expanding. Dark energy exerts a negative gravitational force. That's why Einstein was interested in it. What that means now is that the expansion of the universe is actually accelerating. The difficulty with dark energy is that despite Einstein's early use of it, the theoretical estimates with a more sophisticated understanding of particle physics now imply that either it should be exactly 0 or it should be 60 to 100 orders of magnitude larger than what we observe, neither of which is obviously correct. So the nature of the cosmological constant or the dark energy, why it has the value that it does, I think is one of the major mysteries that particle physics and astrophysics are going to have to solve over the next decades. Nevertheless, even though we don't understand it, once again, we can work with it. If we augment the model of ordinary matter and exotic matter with dark energy, we can ask how well it fits the properties of the universe that we have. You remember I showed this plot of the brightness of supernovae as a function of distance. I said they were a little bit above the curve just for ordinary matter and exotic matter. The curve, if you include dark energy, falls right through the middle of these points, so it fits perfectly. The large-scale distribution of galaxies, the theoretical predictions look like these lines with here and here with this little bump. There's the data. Once again, it agrees perfectly. The age of the universe agrees perfectly with the age of the oldest stars. The small irregularities in the cosmic background radiation, this is technically a plot of the power spectrum of that radiation, those fluctuations depending on angular scale. This is the data, and this is the theoretical prediction, and every little bump and wiggle that you see is exactly reproduced in the data. So even though we don't understand the vast majority of the content of the universe, once we're willing to accept this, we have a model for almost all of the observational properties on large scales of the universe that fits all of the data extremely well. Not only does it fit all the data extremely well, but we can actually make very precise statements about many of the properties of the universe. The average density of the universe is equal to the critical density to remarkable accuracy within better than 1%. That means the geometry of the universe is very nearly flat. That's entirely consistent with the predictions of theories of the very early universe based on what's called inflationary cosmology. Remarkably, we can tell you the age of the universe. It's 13.7 billion years within a couple of percent. The density of ordinary matter is actually 4.2% of the critical density. Uncertainty in that's only 0.2%. On the largest scales, the universe is isotropic, looks the same in all directions to about 10 parts per million or better. So we really have some very precise understanding of the properties of the universe, but an extraordinary lack of understanding of what the nature of these two components are. Let me move on to the last subject that I'll talk about, which is evidence for black holes in the universe, a kind of third kind of object that you don't see on the Earth. The idea of black holes is very simple and very old. It's just that if you have an object that's sufficiently massive and sufficiently dense, even light isn't going to be able to escape from it. It was first suggested by an English clergyman over 200 years ago, but a consistent description of black holes only came about through Einstein's theory of general relativity. The interior of a black hole, the region inside what's called its event horizon, is invisible, and anything that enters the event horizon can never come out again to report on what it saw. Nevertheless, the black hole may reveal its presence because of its influence on nearby matter. That influence would include gravitational lensing. We've talked about that already. Its gravitational force can affect the orbits of nearby stars. And if there's gas orbiting the black hole, then frictional heating from the very strong shear in the gas can heat the gas to a very high temperature where you may be able to see it in X-rays. It's worth remembering that black holes really are very small. The event horizon, if you collapse the sun into a black hole, the event horizon would only be 3 kilometers in radius. So that's the theoretical construction of black holes. I want to then turn to an apparently unrelated phenomenon, which is the quasars. When the first when the first radio telescopes were built and used to make surveys of the sky, they discovered that some of the strongest radio sources were ordinary galaxies, but others were unusual star-like objects that, when you looked at them, just seemed to be point sources of light, just like stars. And that's, of course, the origin of the name. They were called quasi-stellar objects, or quasars. They were first thought to be some sort of unusual star in the Milky Way, but were soon discovered to be not in the Milky Way, but in fact more distant than almost all other objects known in the universe, something like 100 million times further away. Since brightness goes off like the square of the distance, if they're 100 million times further away, they have to be extremely intense sources of radiation. Quasars turned out to be very small, bright objects located in the centers of galaxies. The reason they looked starlight is simply that the quasars were so bright that they drowned out all the light from the galaxy. So quasars, like supernovae, can exceed the total light from all the stars in the galaxy by a factor of 100 or so. What's different is that the supernovae are only bright for a period of a few weeks or months. Quasars shine for millions or maybe even hundreds of millions of years, and therefore the strongest steady sources of energy in the universe by far. This is an example of a couple of quasars. These pictures don't show the full brilliance of the quasar because they've been specially enhanced to bring out the galaxy behind them. You can see these are pretty ordinary looking galaxies with this extraordinarily bright source sitting in the middle of them. One of the other curious features of quasars is that the number of quasars isn't constant. This shows the density of quasars, the number of quasars in a fixed volume in the universe, even accounting for the expansion of the universe, and how it depends on time since the Big Bang. And you can see that the density of quasars about 2 or 3 billion years after the Big Bang is something like 2 orders of magnitude, a factor of almost 100, bigger than it is now. So somehow, in contrast to almost all other objects in the universe, you formed a lot of quasars and then they disappeared. And the peak sort of epoch of quasar activity was when the universe was only 2 billion years old, about 20 or 30% of its current age. The thesis that I'd like to put forward is that these two objects, black holes and quasars, are the same. That is, that quasars are black holes with masses somewhere between 1 million and 1 billion times the mass of the sun that are shining, emitting this extraordinary radiation from superheated gas that's slowly spiraling into the black hole and in turn making it grow even more massive. There's a wide variety of evidence for this. One is that quasars emit jets of particles and radiation. This is actually emitting a jet in both this direction and this one. This one isn't visible because it's fainter, because the jet's traveling so fast that it's dimmed by relativistic effects. Eventually, the jet plows into gas in between the galaxies and makes this huge hot bubble. The time it takes the jet to get from the quasar out to here is about 1 million years, even though the jet is moving at close to the speed of light. And you can see that despite that, over that million-year interval, the jet is absolutely straight. And the reason for that has to be that whatever is producing the jet is an extremely stable, has an extremely stable direction. And a very good way to do that is to have a spinning black hole that sends the jet out along its pole. This is an example of a smaller jet from a relatively nearby galaxy. If you expand the view near the center of the jet, you can see blobs. And if you follow those blobs over a 4-year period, you can watch them move outward. The speed at which they're moving outward is a substantial fraction of the speed of light, and the only way we know to make things that are moving that fast is with the intense gravitational field close to a black hole. Quasars also vary. They're not steady sources. They fluctuate up and down on timescales of months. That says that their size has to be very small because it's almost impossible for a naturally occurring object to coordinate whether it's going up or down in brightness on 2 scales that are separated by more than the time it takes light to travel across that distance, because nothing can travel faster than light. That says that the quasars have to be smaller than the distance light can travel in a month. That's only about 100 times the size of the solar system. We now have even tighter constraints that say that, in fact, the size of the quasar is less than the size of the solar system. So you have to think of these things as emitting 100 billion times the luminosity of the sun from a volume that's smaller than the distance between the sun and Pluto. A final argument for why black holes are the energy source for quasars is simply efficiency. Everyone thinks these days about the efficiency of energy conversion. Well, using Einstein's relation between energy and mass, E equals mc squared, you can define a natural efficiency for any radiative process, which is just the ratio of the fuel it uses times c squared to the energy it puts out. On these standards, our ordinary chemical engines are extremely inefficient. Gasoline has an efficiency that's 9 zeros followed by a 3. Nuclear reactors are much more efficient with an efficiency of about 1 part in 1,000. Black holes are the most efficient engines that we know of. They'll convert something like 10 to 30% of the rest mass energy in their fuel into radiation. As a measure of how efficient they are, if we could solve our energy problems by keeping a black hole in the closet, the black hole could survive all of the US energy needs with a fuel supply of less than 100 pounds a day. The reason this is important is that, as I've said, quasars emit enormous amounts of energy for a very long time. Given their total energy output, the fuel supply that they require, even by astronomical standards, is absolutely prohibitive unless they have efficiencies that are comparable to this amount. Well, if we believe that black holes are the power source for quasars, and if the present abundance of quasars is much less than their abundance early in the history of the universe, and if quasars are found in the center of galaxies, then since the black holes didn't go away, many nearby galaxies must contain inert black holes or dead quasars sitting in their centers. And the next obvious question is, well, if that's true, can we find them? The natural place to look first is the Milky Way. You've seen this picture before. On this picture, in terms of light years, 1,000 light years is something like that distance. If you expand the view of the center of the galaxy, which is where you would look for such a black hole, this is a view on a scale of a few light years. If you expand yet again, you get a view that looks like this on scales of maybe 100 light days. This is an image that was taken in 1992, and astronomers have monitored the center of the galaxy continuously over the last 15 years and watched how the stars move close to the center of the galaxy. So I'm going to show a short video showing how the stars move, and then expanding still further to look on an even smaller scale. So could you run the video, please? Can you run the video? Nope, back. Okay, try it again. Nope, back. Nope. You should be getting a little hand. There. Okay, just click on it. Okay, if you expand inwards, those are the motions of the stars over the last 15 years. The little cross is the location of a radio source, which is widely believed to mark the center of the galaxy. And what you can see from this star in particular is that it's exhibiting the orbit of something which goes slowly out here, much faster here. It's clearly orbiting around some condensed mass close to this point. Okay, can we go on? Okay. If you analyze those orbits, what you find is that all of these stars have to be orbiting an object whose mass is 4 million times the mass of the sun, but whose size is less than the distance from the Earth to Pluto. There's no known object other than a black hole that could have these properties. So we're not getting down to the event horizon. That's much smaller, only about 10% of the Earth-Sun distance, but we're clearly in a situation where we have no conceivable object that we can think of other than a black hole to explain what's happening at the center of our galaxy. You can see this in other similar phenomena in other galaxies as well. This is an otherwise undistinguished spiral galaxy, but it happens to have gas near its center, which is located in a disk and has conditions such that it's acting like a natural laser, or more properly a maser. It's emitting very strong, coherent radiation that enables us to map the kinematics, these spots, extremely carefully. When you do that, you see that the spots here have a speed as a function of radius that looks like this. The dots here have a speed that looks like this. This is exactly what you see, again, from Newton's law for the motion of the planets. It implies that you can calculate that there must be a central mass in here. You can calculate the mass. It's 40 million solar masses with an uncertainty of only 2%. There's no known object, again, other than a black hole that can be that massive and that small. The final argument is that even though you can be confident that you're seeing black holes in the center of, by now, several dozen nearby galaxies, you don't know that those are the black holes that are left over from the quasar epoch. But in fact, there is a very powerful indirect argument that it is. We know how much energy the quasars emitted during the history of the universe. We know roughly the efficiency of accretion of matter onto a black hole. And so that means that the total mass of what you might call ash that's left over from the quasars has to be around 5 to 10,000 solar masses in a box of 1 million light years on its side. You can also go out to all the nearby galaxies. You can ask how much mass there is in the black holes we've found in their centers. It's 8 to 14,000 solar masses in a box of the same size. This agreement is so good that unless it's an incredible coincidence, it says almost certainly that the black holes that we're seeing are the remnants of dead quasars. They're objects that once shone as quasars and now probably have been starved of fuel and are now inert. Okay, let me then summarize. I'll summarize by going back to the simple view of 20th century astrophysics that I described at the start of the talk, that we're not located at a special place in the universe, that the laws of physics that we investigate in the lab govern the behavior of astronomical objects, that the study of astronomy can reveal new laws of physics, and the sun and stars are made of the same elements of the Earth. The first of these, we actually now have a kind of super Copernican principle. Not only are we not a special place or a special time, we're not even made of a special material. The vast majority of the material in the universe is either dark energy or dark matter, and there, in addition to these, there's a small amount of sort of leftover pollutant of hydrogen and helium and all the other elements that we know and everything that the Earth and the stars are made of. The laws of physics that we investigated in the lab govern the behavior of astronomical objects. The prediction of Einstein's theory of relativity that black holes exist has been confirmed. There's now indisputable evidence that very massive black holes exist. The question that we hope to be able to investigate in the next decade or two is whether their properties conform exactly with the predictions of Einstein's theory, which are very strong. We hope to be able to do that by detecting gravitational waves from merging black holes. And finally, one of the most remarkable predictions of theoretical physics in the 20th century, the existence of black holes, has been confirmed by one of the dramatic discoveries of observational astronomy, that is, the quasars. Not only can the study of astronomy reveal new laws of physics, but as the cost of accelerators grows, it's likely that studying astronomy is going to be one of the most powerful, if not the most powerful method we have for discovering new physics in the 21st century. And finally, although it's true that the sun and stars are made of the same elements as the Earth, first of all, most of the universe isn't. And second, ironically, Plato's original idea of an ether, of an immutable, unchangeable fifth element, has now been resurrected. Such an element, if you call it now dark energy instead of the ether, comprises something like 3/4 of the total mass and energy of the universe, and trying to understand its nature and its connection to the rest of the laws of physics is going to be one of the central problems for physics in the 21st century. All right, I'll stop there. Thank you. Peter has told me that I can answer questions until he runs his hand across his throat. Yes. The Institute will make the slides and video of the lecture available on their website. I think that's correct. Yes. Yes. Well, given the puzzles that I've presented, it's of course always good to be cautious. But the statement that nothing travels faster than the speed of light is a statement that follows from the requirements of the theory of relativity and the requirement that events can't be acausal, that is, that you can't go back and kill your grandmother. So at the moment, if we believe Einstein's theory is correct, and that's still only a tentative discussion because it hasn't been fully reconciled with quantum mechanics. It's not just that we can't see anything that travels faster than the speed of light, but you can't have anything go faster than the speed of light without getting into severe contradictions in the laws of physics.
You know, I've been thinking, though, when we're reading about the possible generation of small black holes out of a super collider, that did happen. That would be a ultimate active force energy, throw everything that is
Well, I agree that black holes are very efficient. Not only are they're attractive, not only are they efficient, but if you have things like radioactive waste, you may as well just use them as the fuel, throw them in, and then nothing will ever, then you really have disposed of them. The difficulties are that the black holes that might be created in the Large Hadron Collider are extremely tiny and will only survive for an infinitesimal fraction of a second, and therefore are a very long way from anything that we might be able to use. And of course, the other difficulty is that black holes are pretty difficult to control. Yes?
Dark matter form black holes, if not, why not? And would we be able to tell if it is?
It's most likely that dark matter will not form black holes. One of the attractive features one of the interesting features of dark matter is obviously the reason that it's dark and so difficult to detect is that it doesn't interact electromagnetically with ordinary matter. That means that its interactions are only gravity and possibly the weak interaction. Those interactions are extremely weak, and although in principle you could imagine processes that might make black holes out of dark matter, there's no reason to think that those will happen, and our best current estimate is that the only influence that the dark matter will be relatively smoothly distributed. So you can't rule it out, but nobody has proposed any mechanism by which they could contribute significantly to the population of black holes. Yes. That's a very reasonable point. I think first of all, the reason that the flatness of the universe is not a concern for the Copernican principle is that theories of the very early universe based on inflationary cosmology imply that an early stage of inflation in the universe naturally produces a universe that's extremely close to being flat. What is a problem for the Copernican principle is that in such models, the relative amounts of dark energy and dark matter change with time, and for most of the history of the universe, it's either entirely dominated by dark matter or entirely dominated by dark energy. And it's somewhat anti-Copernican to say that we're in the relatively short fraction of the history of the universe in which there are comparable amounts of dark energy and dark matter. This implies to some people, as the Copernican principle often does, that we're making a serious mistake. But the principle, the whole usefulness of the continuing usefulness of the principle is that it may be telling us that we're making a mistake. Yes?
If the black holes in the Switzerland thing really only survive for a few fractions of a second, how exactly do they die?
The simplest way to see it is that very small black holes emit what's called Hawking radiation after Stephen Hawking. They spontaneously create particles and antiparticles, one of which travels inside the event horizon and one of which goes outside. That means that they're basically emitting radiation. The amount of radiation they emit by this process is totally negligible for black holes of the kind we're talking here, many times the mass of the sun. For the microscopic black holes, that process is extremely efficient, and basically it means that they evaporate on an extremely short time scale. Yes. No. So that's obviously an alternative, and and many people have tried to think about whether you can come up with an alternative theory of gravity. What you'd really like is to come up with one which would explain both dark matter and dark energy in one natural way. Nobody has really succeeded in doing that, and in fact, one of the lessons that we learned from Einstein is coming up with consistent models of gravity that aren't extraordinarily baroque is very difficult, and it's proved very hard for people to come up with compelling theories of gravity that can do away with the dark matter. That hasn't stopped people from trying, and it's obviously an effort that's very worthwhile to continue. But the bulk of researchers prefer to think that there's just some kind of matter that we haven't discovered yet, rather than throw out the whole apparatus of all the laws of physics that we know of. But they might be wrong. Yes. The question was whether the relation that I showed for supernovae was between distance and luminosity, or redshift and luminosity, and you're correct. We can't measure the distance directly. What you can measure is the redshift, which is related to the distance through the expansion of the universe. So really it's a relation between the apparent brightness that you see and the redshift that the system is at. That's correct.
Professor Tremaine, is there a theory about the reason why the dark matter seems to be distributed toward the periphery of the galaxies rather than toward the center?
Yes, that is the belief is that initially, shortly after the formation of the universe, the dark matter and the normal matter was distributed in the same way, but that because the normal matter can interact through, because it's visible, it can give off energy through light. That means that as the two kinds of material collapse to form a galaxy, there's a separation. The ordinary matter can cool, release energy, and sink lower in the gravitational potential, and the dark matter is kind of left on the outsides. So it's not, the way to think of it is not that the dark matter has been pushed to the outside, but that the stuff we see has sunken into the middle. Yes? If we had a quasar in the middle of the galaxy, Nadia knows much more about quasars than I do. I think the answer is no. That is, the center of the galaxy is about, no, the answer is no. It would not be brighter than the sun. The sun is it's obviously intrinsically much brighter than the sun, but it's so much further away that the sun would win. Well, you would have some difficulty because there's so much dust and small particles between us and the center of the galaxy that it would obscure the quasar. But if you went, say, to the next nearest galaxy, to the Andromeda galaxy, and there was a quasar in the center of that, that would easily be visible during the day. Yes? The observations only consisted of the observation that there was what the Chinese called a guest star. That is, the Chinese astronomers said there is a new star appeared. It was very bright, brighter than these other stars, and its location was in such and such a constellation between star A and star B. And the reason we know that's correct is that first, the location that they identified coincides very well with the center of that glowing cloud of gas that we see. And second, that from the expansion of the gas, you can extrapolate backwards, figure out when the gas must have exploded, and it coincides very well with 1054. Yes. In principle, yes, because obviously everything with mass attracts everything else with mass. But although black holes are very impressive, on the scale of the galaxy, the black hole that we're talking about is very small. It's only 1/millionth of the total mass of the galaxy. So in principle, it's correct that there is an interaction. In principle, for instance, the black hole is slowly growing because it's accreting the dark matter. But the scale of the galaxy as a whole is so large and the density of the dark matter is so low that in practice, although both the black hole and the dark matter are dark, they're completely independent phenomena. Okay, Peter is slicing his throat, so thank you very much.